Good. So we briefly spoke about multinomial coefficients. And in multinomial coefficients, if you remember, we have n objects. In this case, let's say in this example, we had 10 knights and 3 categories. So those multinomial coefficients arise when you are assigning to distinct objects distinct destinies. Good. So in this case, we remember what happened there, right? So dragon number 1 had to get a meal out of exactly 3 individuals, 3 knights. Dragon number 2 had to get a meal out of also 3 individuals, and the last dragon had to have 4, right? And then we realized that we can just put them on tray 1, tray 2, and tray 3. And the number of assignments on the tray, the number of destinies, right, will be then, they take 10 factorial knights, divided by 3 factorial, 3 factorial, 4 factorial. Good. So that's already something we spoke about in the last lecture. So that's why we have this coefficient. Any questions on that situation? And in general, that's where we ended up, is that if we have n knights, and then we have R dragons, so where dragon 1 wants to have n1 knights, dragon number 2 wants to have n2 knights, all the way to dragon number R, he wants to have nr knights. The number of possible destinies by which we can assign those knights is n factorial divided by n1 factorial and 2 factorial, all the way to nr factorial. Everything clear? Wonderful, thank you. So now we see how that helps us expand the coefficient x1 plus x2 plus xm to the power of n. We did, in the last class, we covered binomial coefficients. So now we cover multinomial coefficients. Why is that the situation? So if I multiply this sum n times by itself, I have parentheses 1, parentheses 2, all the way to parentheses n. Yes, all the way to parentheses n. And so the possibilities are here clearly. What are they, right? So they're clearly, it's summation over whatever came from, whatever was contributed from parentheses number 1, whatever number was contributed from parentheses number 2, all the way to whatever was contributed from parentheses numbered n. Good? So what we have is a summation, and how many terms are in the summation. So here we distinguish where each object came from each parenthesis. In this case, guys, in my analogy, by the way, let's see if you remember this analogy. The knights here are what? What are the dragons here, and what are the knights for this particular analogy? You remember what the idea, right? The idea, you have some number of objects and distinct objects in general assigned among R different destinies, and each destiny requires a number of objects. So in this situation, what would you think? What are the dragons and what are the knights? Please write in the comment. And show me your faces, goddammit. Thank you, Alejandro. Well, the groups, be precise about it, right? So in this case, we have x1 all the way to xm, and we have a bunch of parentheses. So which of those are the dragons and which of those are the knights in this analogy? So Bo says the knights are the x's. How many of you agree with Bowen that the knights are the x's? You just write yes. So Intrepid agrees. We'll see if we have to go over that one more time in case we don't. So Melissa agrees that the knights are the x's. What about the rabbits among you? Do you agree that the knights are the x's? Okay, so now Bowen changed his mind. All right, and then a bunch of other people seem to be confused. You had too long of a vacation from me. All right, let's again, right? So again, it's all a matter of imagination. Do you understand the idea of the knights that I skimmed over, right? So here we had 10 brave knights, and then 3 of the knights have to go to fight dragon number 1. Another 3 have to go to fight dragon number 2, and 4 will have to go to fight dragon number 3. How do we decide who goes where? Well, we can imagine it's like a school cafeteria, right? I haven't been in one, and you haven't been in one for quite a bunch of months. So what you have is on the school cafeteria, you have this black tray. The black tray goes to dragon number 1. The red tray goes to dragon number 2, and the blue tray goes to dragon number 3. Yes? So I place all the knights. If I place all the knights, that corresponds to 10 factorial. Since each knight is a unique individual, there are 10 factorial distinct arrangements on the trays. But some of those arrangements do not change their destinies, right? So if knight number 1, 2, and 3 are on tray 1, it doesn't matter in which order they appear, correct? So that means that we can, for any given permutation, we have 3 factorial times 3 factorial times 4 factorial repetitions that correspond, so changing of the permutation. So there are 3 factorial, 3 factorial, 4 factorial permutations that represent the same exact destiny. Good? So what we do is that we then divide all the permutations by the number of synonyms. So each permutation is a word describing a destiny. So each destiny has 3 factorial, 3 factorial, 4 factorial here, distinct synonyms that describe exactly the same situation. So you take the number of words, which is 10 factorial, and divide by the number of synonyms. And that gives you the number of meanings. Each meaning in this case is a unique destiny, which knights go where. Good? So if you understood this explanation from now and before, guys, please type Y if you're lazy, or yes if you're a little less lazy. Okay, Malika, wonderful, right? Mm-hmm. Yes. Not everybody is here, for example, right? So I haven't seen everyone understood it. Sayed, thank you. Alejandro, yes, thank you. And then if you understood this analogy, I hope you understand why you divide. We kind of talked about it in previous several classes, right? Very important idea. Must be completely not confusing. So back to the general situation. In the general situation, we have R trays. And the first tray will have to contain N1 and sub 1 knights. Second tray has to contain N sub 2 knights, and so on. Okay? So the general situation will be N factorial, which are all the permutations arranged linearly, divided by N1 factorial and 2 factorial all the way to N sub R factorial. Because we just have the same idea, right? We just now have the denominator represents the number of permutations that represent the same outcome. So we divide the number of words by the number of synonyms to get the number of different meanings. That's the analogy. Because in this case, unlike in English, you always have the same number of synonyms per each meaning. So you can divide. So back to this analogy again, guys. I'm asking you, when I expand the parentheses, right? So what happens here, right? So outcome number one represents what did the first parenthesis contribute, okay? The first parenthesis can contribute either x1 or x2 all the way to xm. So outcome number 1 represents what parenthesis 1 contributed. Outcome number 2 here represents what parenthesis 2 contributed, and all the way to outcome number n, that will represent what parenthesis numbered n has contributed. Good? So when I expand this, I realize that I always have a product and I have summation of those products, and each of those terms that I'm adding, each of the summands contains exactly one term from parenthesis 1, exactly one term from parenthesis number 2, and so on, exactly one term from parenthesis number n. Yes? So again, the question is, in this analogy, if you see, you kind of have to see combinations here. Who are the knights and who are the dragons here? Do you see that analogy, guys? It's the same situation, truly. Okay. So Shaw is saying that n is the number of dragons and m are the number of knights here. Do you agree with Shaw? Okay, Naomi says she agrees. Melissa agrees. Erica agrees. Okay, a few. Paula agrees. Inan agrees. Does anyone disagree? Careful, careful. First, do you see the analogy here? Yes. Well, guess who doesn't agree? I don't agree. So think about it. What happened here, right? What is parenthesis number 1? Parenthesis number 1 is what's happening over here. It tells you in the summation, well, parenthesis number 1 was attributed to x1 or to x2 or to x3 or to x sub m. So the parentheses here are the knights and the dragons are the x's, because you understand, I mean, I see the analogy here. So 1, that is the fate of knight number 1. What happened to knight number 1? Was he eaten by dragon number 1 or dragon number 2 or dragon number 3 or dragon number m? That you can see, you can just write a code here. That's how you know. So 1 is the fate of dragon number 1. 2 is the fate of, 1 is the fate of knight number 1. 2 is the fate of knight number 2. N is the fate of knight number n, right? You should listen to My Favorite Lullaby, then you would have understood it entirely. It's about exactly 3 knights. One was eaten by wild beasts. The second was killed on the way, and the third forgot the name of the person he was supposed to meet. It's a very beautiful song. If I might show it to you at once. Okay, it's much more pretty than what I described in my very crude translation. So those boxes describe what happened here, the fate of each knight. Okay, and so we sum over all the possible fates, what happened to each of them, right? So then the question is, first of all, how many terms do we add? Do you see, guys? It might be a weird analogy. You think, oh my God, what? But you see, the idea is that when you count, you have to realize, well, how a code communicates a meaning. And the easy meaning here is to say, the parenthesis here contributes either x1, x2, or x3, or all the way to xm, and that can be interpreted as saying that knight number 1 was eaten by dragon 1 or 2 or m, right? That's the idea. So first, using this, how many terms do I actually add up? So if I expand it and I do not simplify like terms, how many terms are part of the summation? Melissa, n terms, well, in the entire summation, right? Clearly each part that is added, you're correct there, right? Each part that's added has n terms, but the summation will be one bunch of n terms plus another bunch of n terms plus another bunch of n terms. The question is, how many terms are we adding? How many summands, right? So how many terms are there between which we see pluses? That's my question, right? So each thing that you add, each chunk is a multiplication of exactly n terms. Okay, interpret says m to the power of n. Do you agree? If yes, you write yes. I want to see how many understand it. Well, you're trying to calculate how many terms, right? I'm asking just without simplifying, how many terms are we adding here? Wonderful, Melissa. Wonderful, the people that noticed it. So think what happens here, right? So how many possibilities for the first box? First box can be m possibilities, second box m possibilities from the second parenthesis, all the way to the last box, it has m possibilities. So we multiply m by m by m by m n times. So it's m to the power of m terms that we are adding together. Do you see that? Yes, I say I cannot see all your faces and not all of you respond. So let's see. Type yes, or I don't know, I'm looking at some of you. Yes, good. Good, Malika. Wonderful. Wonderful, right? If you understand this pretty impressive feat of imagination that you have. So now the more challenging part of this question, okay? So we agree that additions are m to the power of n, because that's why I made the boxes here, right? Each parenthesis ends up contributing one term. And if I don't simplify, I see exactly m to the power of n terms that are added. Good. Now, suppose that I want to group by some category. So let's say I want to find how many terms are of this form: x to the power of some n1, x2 to the power of n2, xm to the power of n sub m. Yes, I want to know how many terms are of this form. But you see, we had this idea about the dragons. What are those terms? What does this term mean? It means that exactly n1 knights were eaten by dragon number 1, and 2 knights were eaten by dragon number 2, all the way to n sub m knights eaten by dragon number m. Yes? Good? So how many terms are there? So how many terms of this form are there, right? So that means assign, choose out of the n knights, I have to choose n1 that will be going to dragon 1 and 2 going to dragon number 2, all the way to nm of them going to dragon number m, which means this is the number of terms of that form. N, choose n1, n2, all the way to nm. You understand? It's hard to group them like in the binomial theorem, but if those are the powers, that means that those are the groupings. That's how many were attributed to dragon 1, to dragon 2, to dragon m. So we now have a formula for the multinomial coefficient. Let's see if you can play this game. So this is maybe a difficult question. Are you ready, guys? So A, we have 9 pupils. They are to be divided into 3 teams, each consisting of 3 players. So one team has to wear a red shirt, the other team has to wear a blue shirt, and the last team has to wear a green shirt. The question is, how many team assignments are possible? So go ahead and try to calculate it, guys. How many team assignments? 9 pupils, 3, 3, and 3. Okay. Oh, 9 people are already available. Wonderful. Wonderful. You are very quick, aren't you? Beautiful. So let's see. Everything I see so far looks absolutely correct. Yes, absolutely correct. Now, why is that the situation? Now we have 3 dragons. One is the red dragon, the blue dragon, and the green dragon. Each requires exactly 3 pupils. Same thing, shirts, jersey shirts that they will be wearing. It's like the dragons that will eat the knights. So what we have is 9 individuals to be assigned among 3 destinies. In each destiny is different from another, correct? So that would be 9 factorial divided by 3 factorial, 3 factorial, 3 factorial. Good. Here is the situation is getting slightly more complicated. So now only red shirts arrived. So the other 3, so 3 players will be assigned the red jersey, and the other players will not be assigned any distinguishing shirt. Understand? They will not be assigned a short. How many possibilities are there now? Okay. So Melissa, let's see what you said here. Be careful. Be careful, guys. You see, that's what I mean. You have to construct a Kafka protocol. The Kafka protocol will ensure that you are not making a mistake. You have to have a very good visualization of the code. Interpret, thank you. You have to have a good visualization of the code. Even if you can solve this problem without it, there will be other problems where you might face a more challenging time. Okay. Okay. Right, Bowen, and thank you, Erica. All right, so let's see first of all, what is my Kafka form for the first problem, right? So it's like this. Here is how I imagine the document to look like. What I will do, I will assign the 9 pupils. I will label them 1 through 9, and I will always order the numbers that I write in the red segment in order, in the blue segment in order from smallest to largest, and the same for the green segment. So for example, suppose that 2, 5, and 3, individuals 2, 5, and 3 were assigned to the red jersey, 9, 1, and 4 to the blue jersey, 7, 8, and 6 to the green jersey. So the input code that I put here is 2, 3, 5, because you see, I have to put them in order. 1, 4, 9, 6, 7, 8. Okay, you understand? So the red numbers have to be in order from increasing from smallest to largest. The blue numbers must be from smallest to largest, and same for the green. You see that? Now, all I need to do is now figure out how to count the number of such codes. You already notice that it's simply 9 factorial divided by 3 factorial, 3 factorial, 3 factorial, or 9 choose 3, 3, 3, the multinomial coefficient. I hope that makes perfect sense to you. We developed a way to count such codes. Good? Now, what happens using the same, so you notice some of you already, so few of you gave me the right answer, but some of you made a mistake. Why was that mistake made? Because you were not thinking about this Kafka form. Now, what happens when I apply the Kafka form? I have the same boxes, but I cross out green and blue. So that's no longer a different category. Do you see that? And when I cross it out, what happens? So for example, I can still put the same codes as I did before. I can put the code 2, 3, 5, 1, 4, 9, 6, 7, 8. But that code corresponds to exactly the same situation because 1, 4, 9, and 6, 7, 8, I can just color them black now because there is no distinction between this group being in the middle and this group being at the end, or if I reverse the order, right? So I can take this chunk and move it around. I can uncouple the boxes and I can move them around like this. Do you see that? Which means in terms of synonyms that if I use the same form, the code 2, 3, 5, 1, 4, 9, 6, 7, 8 is the same as 2, 3, 5, 6, 7, 8, 1, 4, 9. I can just change places here. Do you all see that, guys? What I'm trying to convey here? So if I already counted the previous situation, I have a document printed for each of the previous situation. Now suddenly there are no blue or green shorts, which means I erase those in the indices, and suddenly documents that have different codes. You see, this is definitely not the same code as this one, right? But they correspond to the same exact situation because that says there is a red team and there is team and team. That's all I can say. Who is a member of a team? That's all I can tell now. I cannot distinguish the category to which the team belongs. Is it the green or not? I don't know. So I can move the codes around. Are you following? So that means now that from the 9 factorial divided by 3 factorial cubed documents, exactly 2 documents correspond to the same destiny. So I need to divide by an extra 2. You follow my explanation? If yes, please type Y, that you understood what I just said. Okay. If they were different sizes, yes, it would. It will be, of course, not possible to change their positions. You see what I'm saying, guys? It's just I think in terms of code. So what I truly imagine is that I was already able to compute the previous situation because I developed a tool for that, right? So I imagine a pile of documents, and each document means a different thing altogether. But suddenly, if I don't have blue and green category, I cannot tell who is blue and who is green. So documents where in the middle box I have the number, let's say 149, in the last box I have 6, 7, 8. If I change positions of middle and last, the destiny isn't changed. It's still the same teams. So 2 documents become suddenly the same meaning. They suddenly have the same meaning. And then another 2 documents suddenly have the same meaning. So what I have is that each meaning that I can interpret here has 2 documents from the pile. So I take already know how many documents are in the pile. I divide it in 2 to see how many meanings I have. Good? It's just being careful with this type of thinking. And here is a comprehension check. So here you have no shorts arrived. How many possibilities now, please? Okay, Bowen, you have Bowen, you have 3 factorials and a 3. Eric, you have 4 times 3 factorial. Paula, 4 of them. Okay, so so Alejandro says, wouldn't you multiply that thing by 1/3? Well, don't ask me. 1/3 factorial, possibly. Good, Alejandro. Okay, good. Any other answers? Melissa, you say a 3 at the end? Okay. Bowen, thank you for the correction. And here is the solution, guys, okay? So you have to think of, in terms of the codes, you divide by 1/3 factorial, because you see, you might say over 3, but think about it. How many ways can I uncouple the boxes and rearrange them, right? There are 3 factorial rearrangements. Think about this code. You see this code? How many ways can I interchange it to get a new code? So I have this 9, choose 3, 3, 3, but I have this red chunk, blue chunk, and green chunk. How many ways can I rearrange it? Well, there are exactly 3 factorial ways to rearrange it. You agree? Because I can just, how many ways are there to put this chunk first, second, third, or in any other order? You can construct a separate document and count it if you are confused. You understand? So you ask yourself, you see, once you have a particular code, it's item 1, it's item 2, it's item number 3. How many ways are there to order 3 items? There are exactly 3 factorial ways of ordering 3 items, correct? So now suddenly the meanings we had, each meaning has 3 factorial or 6 words corresponding to it. Good? Are we getting it, guys? You see why it's 1/3 factorial? It has to be extremely not arbitrary. Whenever you're confused, you have to construct a document or imagine constructing a document and just visualize perfectly what you are counting. All right, so let's move to the next lecture. So counting with, so here this lecture is called Distributing Identical Objects Among Non-Identical Destinies. So this is a problem that I thought when they started this lockdown, people started hoarding toilet papers. So you have 5 toilet papers, identical toilet paper rolls, to be divided among 6 hypochondriacs. How many partitions are possible? Where of course each toilet paper roll looks exactly like another toilet paper roll. And one person that actually worked as a cashier inspired me to explain it this way. Okay, so we want to know what's the number of integer solutions to this equation: x1 plus x2 plus x3 plus x4, x5, and x6 equal to 5, where xk, let's say x1, is the number of toilet paper rolls that will be given to hypochondriac number k. Make sense? So we have 6 hypochondriacs, and of course some of them obviously will get no toilet paper rolls at all. So xk is between 0 all the way to 5, right? So maybe there is a possibility that x1 gets all of them, or maybe x6 gets all of them. Okay, so I have never worked in a grocery store, and I am terrible at counting. You see, I mean, you see, when I have to give changes, I'm like that old Russian man that stays actually near my cashier store. You should have seen this guy, right? There's a huge, terrible line. There are like, 15 individuals, and he talks to them in Russian, right? And I joke with one of them, you see this girl, she was kind of American, and you know, she was very impatient, and she was speaking to him in English. I say to the guy next to me, "You just wait. It's called cultural immersion. In a moment, she will start speaking Russian." And to my surprise, she spoke. In the next 2 minutes, she spoke perfect Russian. You see? And you know what he does. There's some guy obviously that is not Russian. He comes to the cashier and he says, "Ну чего ты стоишь? Ну давай, ставь это сюда. Ну ставь продукты сюда." And he expects this person to understand, right? So that's called cultural immersion. So such things remind me, yeah, you see, that's the best way to learn a language, right? So if I start speaking to you in Russian, that's my belief. By the end of this course, if I taught it in Russian, that's the language you will be speaking. So in a grocery store, you have the following situation, right? So you can put the items that you are buying on this road. What do you call this thing? You know, you have this rolling road, and you partition your groceries from the groceries of your neighbor with a bar. Do you agree? So imagine that you have this camera from above, making sure that nobody steals anything. And this is what you see. So the hypochondriacs, they place their toilet paper rolls on the road, and this is the start of the road, and this is the end of the road, and we have blocks, identical blocks that you know, they partition what the person gets. So for example, from the start, I just need one partition. That whatever is between start and block number one is how many toilet paper rolls are going to be given to hypochondriac number one. Yes. Then the toilet paper rolls between bar number one and bar number two, they're not numbered, they're just placeholders, right? So between them, that will be how much X2 is getting. And then between 2 and bar number 3, that's how much the third person is getting, and so on. You understand that? So this situation means what? It means first person gets 2 toilet paper rolls, second person gets none, third person gets exactly 3, fourth gets nothing, fifth gets nothing, and sixth gets nothing. So before I move on, guys, I do not see you at the same time. Are you following what I'm saying? I'm not just like that Russian person is saying, "Ну чего ты ждешь? Ну положи предметы на стол." Right? I'm not like that. Yes?
Yeah.
Thank you, guys. I'm glad that you are following. Yeah. Today is an odd day. So, okay, so then understand the following. The toilet paper rolls are represented by circles. I cannot distinguish one from the other. And the bars, definitely, I cannot distinguish them one from the other, okay? But what can I distinguish? I can distinguish the spaces, you understand? So I create this code. Maybe it's called a barcode in some sense, right? So I have those items, and I have circles and bars, and that fully determines the partition, a particular partition, right? So how many toilet papers? There are 5 toilet papers. How many bars do we need? Well, we don't need a bar for start, and we don't need a bar for the end, okay? But we need, if I select 1 bar, I partition the toilet papers into 2 categories. If I select 2 bars, I have 3 categories. Do you agree? I need to partition, I need to see what each hypochondriac is buying, and they can be buying nothing, right? For that, I need to partition into 5, with 5 bars, into 6 categories. Therefore, I need 5 bars. Are you following me? So 1 bar divided into 2. 2 bars divide the entire, you know, the entire batch of toilet paper into 3. And if I have 5 bars, I divide into 6. So this now becomes a word. And in this word, I have 5 letters of the type and another 5 letters of the type. So there are 10, the word consists of 10 items. So I have 10 factorial divided by 5 factorial. 5 factorial is how many meanings I can get from it, right? Another way to see that, if you prefer, is in terms of spaces. I cannot distinguish certain objects, but I can distinguish which space. So I have space 1 all the way to space 10, I believe, right? So there are 10 spaces, correct? Because I have 5 bars and 5 toilet paper, so I have 10 spaces altogether. I can distinguish which of those 10 spaces are occupied by by a bar and which of them are occupied by a toilet paper roll. Okay, and that fully determines the pattern. So the answer can be given as follows, right? So 5 plus 5, those are the spaces. 5 spaces will be occupied by toilet paper rolls and 5 spaces by the bars. And then I have this the dragon situation here, right? So I have two dragons. One is the dragon that will basically that will eat spaces assigned to toilet paper. So toilet paper is one type of dragon requiring 5 items, and there is a bar dragon, right, which requires also 5 spaces. So we have 5 spaces going to toilet paper rolls and 5 spaces going to bars. Another simple way of answering this is simply 10 choose 5. 10 spaces choose 5 to mean either 5 spaces that I choose for the toilet paper or the 5 spaces I choose for the bars. Do you understand my explanation, guys? If you do, please type yes. Or if not, I'm happy to explain again. Only 2 yeses, that means that some of you don't follow it. And guys, don't hesitate and ask me to re-explain.
So, Professor?
Yes?
So the 5 and 5 at the bottom collapse into that 1, 5 because we only need to be counting one of those?
Because as soon as I know, if there are only 2 categories, I know that whatever goes to one dragon doesn't have to go to the other dragon. So that's the select, right? So this red 5 means the 5 spaces that will be eaten by the toilet paper dragon. And this 5 means the 5 spaces to be eaten by the separating bar dragon. You understand?
Okay.
Yes. So what I need is simply saying how many of the spaces go to the bars. So I have 10 choose 5. I can put it in black, or if I put 10 choose 5 in red, if I put a red here, that means I decide how many spaces, or which spaces to be precise, go to the toilet paper. Okay. Regardless, it's 10 choose 5. Make sense?
Okay. I think I got it.
Okay. Cool. It will change, Naomi. Of course, it will change if there are only 5 people, right? If there are only 5 people, I need fewer bars. If there are 5 people, I will need 4 bars. So toilet paper is the same, but this will be 4. Okay. Now let's see if you can do it in general, guys. You see? So the general situation, we have n toilet paper rolls, and we have m hypochondriacs, where m is not bigger than n. Okay? I want you to tell me how many arrangements are possible, if you understood it. Please write me a formula. Murshika, do you mean divide by a -1, or do you mean something else? Okay, I see. Thank you. And don't be afraid to speak, guys. Right? I'm happy to hear your voice, at least. Otherwise, it's not so lonely here. I'm sure I will be the last person to get corona here. Okay, Naomi, thank you. When you're ready, guys, just type either you have the solution or write yes for ready. All right, so a bunch of you are ready. Let's see the solution. Again, we are interested in the number of integer solutions, well, non-negative integer solutions to this equation, where each x represents the number of toilet paper rolls attributed to that particular label, right? So how many toilet paper rolls does person number 2 get, etc. So here we need to calculate how many total spaces do we need, right? How many bars do we need? We have m individuals, so we will need m minus 1 bars. Do you agree? We have start and finish, which we don't consider as bars, and in between we have to partition by n minus 1 bars. Because 1 bar partitions to 2 groups, 2 bars into 3 groups, so I have to have 1 bar less than m to partition into m parts. So m minus 1 bars, and total number of spaces are the spaces for the n objects, the toilet paper rolls and the bars. So altogether I have n plus m minus 1 spaces. And the slots of those spaces assigned to toilet paper will be n, and the slots assigned to bars will be m minus 1. Good? With me, guys? So we have this is the multinomial way of writing the solution. Multinomial way of writing the solution. So I have this pattern, which is just how many spaces. This is the distinct spaces. Spaces numbered 1 through space n plus m minus 1. So I can assign I can decide how many spaces I assign to n. So that's one way to write the solution. And that's another way to write the solution, and they are exactly the same. Agreed? Exactly the same. So this is selecting the spaces for toilet paper, or if you select the spaces for the other category for the bars, you know exactly which other spaces went to the toilet paper. So they are complementary. They give complementary information. So this is the full information in multinomial coefficients, and this is just the way you wrote it in binomial coefficient, right? Multinomial coefficient is just binomial coefficient. Sorry, is multinomial with only 2 categories: selected and not selected. Good. So those give us the same solution. Now, right, this is what I always think about with the next problem. It's pretty much what we just did before, and I hope therefore you read The Little Magic Girl. Have you? I sent you a short story. It's 3 pages to read, so you know what the story is, right? So how many of you, by the way, bothered to read it? Just say yes if you have, just out of curiosity. Yes. That's very nice. Only you. You know what I did in the last class that I taught probability? I think since we're doing probability, we might as well read Dostoevsky's The Gambler, and I assigned this book as a reading. maybe I'll do it for this class. The only thing that I am bothered by is I sometimes get the feeling that people find synopses, or just even for rather obscure questions that I ask, that they haven't read the book and just copied each other's solution there. Well, we'll see what I do with it. I think I will just send you this book anyways. It's a pretty good book, one of my favorite. So this is the situation here, right? So we have this little match girl. She needed matches so that she could stay warm. So suppose that that what you're trying to do is this, right? You have m girls and n matches. Make sense? M little girls, and I'm assuming that little girls for you are distinguishable objects, right? Sometimes it's not, right? But and matches are not distinguishable objects. So the question is, how many ways can you donate n matches to m little girls that need it? And in A, the question in A, you are allowed to give some girls no matches at all, but in B, you have to be more generous. You have to give each girl at least one match so that she would be warm for at least a little bit. Okay? All right, Erica, thank you. You're pretty fast. Let's see what about B. Wonderful. Interpret. Very good. So for A, we should not have too much problem, correct, guys? So you understand, right? We have m girls and n matches. The girls, I guess I can distinguish. The matches, I cannot. So what are we doing now, guys? A, you figured it out, but B, you are having trouble. Okay, Erica, wonderful idea. Let's quickly go over A. A is something we already did before. So we can imagine the following situation. We have n matches, and if we buy those matches and they are laid on the on this moving road, what is it called? I don't know, right? This moving road that you have there at the cashier, then you need m-1 bars. So what you can do is you can select n plus m-1 bars. That's the spaces. Conveyor belt. Thank you, Melissa. Here you go. Right? I forgot this word for some reason. Right? Well, early signs of Alzheimer's. So the conveyor belt. So we have n plus m-1 places on the conveyor belt, and out of those places, I need to choose m for the matches, n for the matches. So that's the solution. You can do this, or instead of n, you can place here m-1. Okay. Now the question is, what do we do if we are not allowed? This is counting possibilities where some of the girls might not be getting any matches. If we are not allowed to do that, each girl has to get at least one match. This is what I suggest we do. Do you need to think about it more, or would you like me to go over it before I continue? So you're thinking about it longer, or you want us to talk about it together? Okay, let's talk. So here xk has to be bigger than 1. Here is one possibility to solve this directly, right? So in this case, I only consider spaces between each match. So I arrange the matches 1, 2, 3, all the way to n. There are n matches. And then I put a wedge between those matches. Those are the spaces I will select. So I have space 1 all the way to space n-1. Do you agree? Because after the first match, I have a space. After the second, I'll have a space. I'll have spaces all the way after the n-1th match, but I will not go beyond the nth, right? And notice what happens. If I select, let's say, this space, if I select one space, that partitions into 2 piles. If I select 2 spaces, that will automatically partition into 3 piles. And by arranging the spaces that I selected in order, that tells me exactly which matches go to which girl. Good? So I have n-1 spaces. Out of them, I will choose m-1 spaces, because choosing a space partitions into 2 piles. So if I choose m-1 spaces, that will partition into m piles. Do you understand? So the answer, for example, this is one situation, right? Let's say I had 5 matches and 3 girls. 5 matches and 3 girls. Now I need to have partition into into 3 categories here, right? What goes to girl number 1, what goes to girl number 2, and what goes to girl number 3. You can see that if I select, let's say, space 1 and space 3, then girl number 1 gets a match, girl number 2 gets 2 matches, and girl number 3 gets 2 matches. Make sense? So it's enough to select, in this case, two spaces. So in general, if I have n matches, I will have n minus 1 spaces between them, and I will choose m minus 1 spaces between them. And here is the general approach, okay? I hope you would like one of the questions that I have over there. The general approach is, what do you do if, let's say, you are asked to solve an equation, to find how many solutions are there to the equation x1 all the way to xm equal to n, where each xk has to be bigger than some integer n sub k. How do you solve that equation? Okay, so you understand that means that x1 might be negative, might be positive, who knows, right? But there is a particular requirement which is neither 0 nor 1 necessarily. Okay, so here is what I can do. Understand, each xk is bigger than n sub k, or equal to it, right? And I know how to solve the equations if each xk is bigger than or equal to 1. So this is what I will do. I will subtract from x1 and 1 minus 1. Why do I do that? Is because then this thing in parentheses has to be bigger than or equal to 1. Do you agree? If x1 is bigger than or equal to n1, then whatever is in this big parentheses is bigger than 1 or equal to it. Similarly, I subtract from the second variable, I subtract n2 minus 1. Good? And now this big parenthesis is bigger than or equal to 1, whatever the solution. And I do the same for all the way to xm. And of course, I have to balance the equation. So if I balance the equation, I have to subtract from n those same numbers, okay? So the result is this. The result is that when I do that, it will be n and minus, the one here is repeated m times because I have m categories. So it's the same as n plus m minus n1 minus n2 all the way to minus n sub m, okay? And see the solutions to this new equation, the solution to the old equation are in one-to-one correspondence with solutions to this new equation with the y's. Yes? Yes? So that's what we get here. So then we know already how to solve it, right? We just take this number, subtract 1 from it. You see here, each yk is bigger than or equal to 1. So we take this number, subtract 1 from it, and choose the category minus 1. That's the general solution. Let's try to apply this to this last example, guys. So let's do this last example and we'll be done with this chapter. So you owe the mob at least $10,000 and you have to pay it this week, okay? And your bank account is empty. So then you recall that there is a prize collection of silver spoons in your family. You have 2 of those spoons, your grandma has 6 of those spoons, and your parents have 4 of those spoons. And each spoon is worth exactly $1,000. They are the same spoons, let's say, right? Or at least they look to you like the same spoon. So the first question is this, okay? In how many ways can you pay the mob if you have to steal as little as possible of those spoons? That's your requirement. Obviously, you have to steal from your family, or you only have 2 spoons, correct? And the mob requires that you pay at the minimum 10,000. Okay. as little as possible, to be precise here, means that you will give away all your spoons. Okay, otherwise the question might be confusing. Are you ready, guys? Or completely stuck? Completely not sure what to do here? All right. Let's see what it is. Before the next lecture, there will be some problems I'll ask you to solve so that you will have time to think about them, okay? So this is the way I was considering this problem, okay? So what does it mean to steal from your grandmother? It means that x1 can be a negative number, right? So let's say if x1 is -1, that means you stole 1 spoon. If x1 is all the way to -6, it means you stole -6 spoons, right? So x1 can be up to -6. You might even give your grandmother spoons. It's a possibility here, right? But that's why x1 could be positive. But x1 has to be at the very least -6. x2, the number of spoons in your family, is -4. And x3 is the number of spoons that the mafia will get. It has to be 10 or more, correct? And what you do is you will give away your spoons. So that means that x1 plus x2 plus x3 equals to 2. You agree? The number of spoons that that were distributed will equal to 2. So what that amounts to is, you see, according to my formula, is it's this, right? It's 2 plus 3. The 3 comes from this category, plus 6 plus 4 minus 10, and then I put -1, and then I put the category -1, which is sub 2. So it's 4 choose 2. There are 6 possibilities. And in the next problem, maybe you'll think about it before the next class, right? So here, it is not a priority for you what you take from your family, right? You might take some for yourself. You might give it, you know. So that means that, well, think about it, what that might mean. Okay, so let's call it a day. Or do you want to work on it and then we can solve it together? You understood the idea of this equation here, right? How did I think of it?
So, I'm still a little confused about how you got the 2 plus 3 plus 6 plus 4 minus 10 minus
simply
1.
I updated this equation. Let's first of all see what we tried to solve here, okay? So the idea is that you will not keep any of the spoons to yourself, agreed? You're not gonna keep any of those spoons to yourself, but you have to pay the mob, which means whatever you give the mob, it's at least 10, right? At least 10 spoons will be at the hands of the mob because that's a requirement. Now, what can you do? What are your options, right? You can give spoons in any which particular way you like. You can give some of them to your grandmother or take from your grandmother, right? You can give some to your parents or take from your parents. So what are the what are your options? Definitely, if you indicate like this, right? If x1 is a negative number, if it's 0, that means you took nothing. If it's -1, you took 1 spoon. If it's -2, you took 2 spoons. You understand what I mean, right? So this is how many spoons you took. So it's a negative number because of it. X2 is how many spoons you can take from your parents. Okay, and so what happens here, right? So the number of spoons in this category plus the number of spoons in this category plus the number of spoons in this category equals to 2, because your 2 spoons were given away. Okay, so yes, so that's so then how many ways are there to solve this equation? So the number of ways to solve this equation is the same. What I can do is, instead of having a -6 here, I move the -6 across and I add a 1, okay? Because I want it to be not from 0, but from 1, let's say, right? So it's x1 minus 6, it's x1 minus 6 plus 1, okay? And this is -4 plus 1, and this is -3 plus 1, and then I update this 2. This 2 is updated in according to the formula above. I just have to add 3, which is the number of categories. Just think about it, because if I update, that's the idea here, guys. I make the equation, each of the x's is bigger than or equal to 1, and I know how to solve equations when they're bigger than or equal to 1. You understand? To solve this equation, solution to this equation is equivalent to a solution of the equation where y1 is bigger than 1, y2 is bigger than or equal to 1, and y3 is bigger than or equal to 1, but where I updated each of the variables like I have done in here. You understand? So that they will be bigger than or equal to 1. I reduce the system of equations that I have to solve to one that I already know how to count, where I know how to deal with, okay? So that's the situation. That's where I got this particular formula. And yes, and then you can think about what happens in part B. Good. You understand what the idea here is? Why is it equal to 2? Is because I'm going to give away those 2 spoons, just like I gave away the matches to those girls. I'm going to give the 2 spoons. I'm not going to keep the spoons to myself. That's why I set it equal to 2. I'm generous here, right? But yeah, no worries. If you have to go, guys, you can go, right? And then what happens is that in this case, x1 I can actually make a negative, which means I'm not going to be generous there. I can actually take. If it's a negative number, it means I take. I give interpretation to each solution, right? So for example, if x1 equals to -6 and x2 equals to -2, right? And you understand, right? So those are and then no, in x2, sorry, because it has to equal to 2. So maybe I can have x1 equal to -6, x1 equal to -2, and x3 equal to 10. That would work. Okay. So that's what I mean. The 2 spoons, they will be not kept by me. That's the idea of this equation. And then you might think, what do I do if that's not an issue, right? I might want to keep as many spoons as I like to myself or not. So B obviously should have more solutions. Good. So what do you want to do, guys? If you want, we can call it a day. If not, you can sit and try to solve it. I think I will stop this lecture at this point. I will stop recording, I mean, right? And then you can continue thinking of it if you want.